lab, we will continue with the time series data analysis of the collected data from the public transport network around Auckland region. In this lab, we will be looking at the forecasting. So previously, we looked at finding the missing values using different methods. We looked at the forward fill method. We looked at the backward fill method. We looked at the interpolation, linear interpolation method, and we also looked at the cubic interpolation method, and we also looked at the K and N mean method for n nearest neighbors, and we also looked at the seasonal mean method, and we found out that the linear interpolation method gave us the lowest mean square error. So linear interpolation method was the best method to use to find the missing values. Now, for the forecasting, in this lab we will be looking at the forecasting. Forecasting is the next step where you want to predict the future values the series is going to take. Forecasting a time series can be divided into two types: univariate, using previous values of the time series to predict future values; multivariate, incorporating external predictors to help inform the forecast. We will work with the commonly used ARIMA. ARIMA is auto-regressive integrated moving average algorithm models. This algorithm assumes that the past values of the time series can alone be used to predict the future values. We won't cover the mathematics in any detail here, but simply put, there are four terms of interest. P represents the auto-regressive term, Q represents the moving average term, D represents the number of differencing required to make the time series stationary, and S represents the seasonal term if the time series has seasonal patterns, seasonal autoregressive integrated moving average. We will make our lives easier and use an automatic autoregressive integrated moving average forecasting, although you would typically want to define these parameters yourself after some investigation. Let's look at the reconstructed data frame. So we have the month, year has the index, and the columns are the seasonal column, the trend column, residual column, and there is a actual values column, and the sum check column checks that seasonal finds the total of seasonal column, trend column, and residual column. So we can see that actual values equal sum check values. So now let pre-COVID equal reconstructed.copy open and close bracket. So printing the pre-COVID data, we can see that the month year starts from 1st of July 2005 and ends at 1st of February ends on 1st of February 2020. Let prediction underscore column equal trend. Printing the prediction underscore column. So these are the actual trend values, and that is trend. Import PMD ARIMA SPM. Let model equal PM dot auto underscore ARIMA of pre-COVID column is prediction column and prediction column is trend. So pre-COVID of we can just put trend here instead of prediction column. And yeah, so here when we run this, we'll get okay. So we don't need to add all the parameters here. Okay, so what we have done is that pre-COVID of trend, comma, start underscore P equal 1, comma, start underscore Q equal 1, test equal IDF, use IDF test to find optimal D, max underscore P equal 4, let max underscore Q equal 4, that's maximum P and Q. Let M equal 1, frequency of series. Let D equal true, let model determine D. Let seasonal equal true, no seasonality. Let start underscore capital P equal 0. Let D equal 0. Let trace equal true. Let error underscore action equal ignore. Let suppress underscore earnings equal true. Stepwise equal true. And printing the model. So we see that the best model is ARIMA bracket 3 comma true comma 0, and then bracket 0 comma 0 comma 0, and then in the square bracket we have 0. Total feed time is 2.286 seconds. We found the best model from the lowest AIC value, and lowest AIC value is 1506.796. Print model.summary. Number of observation is 176. Dependent variable is Y. Model is S ARIMA X of 3, 1, 0. Log likelihood is minus 748.398. So AIC is 1506.796. BIC is 1522.620. HQIC is 1513.215. And then intercept coefficient is 6.0584, and from the so we have standard error, we have Z value, and P greater than Z 0.014, and the P value is 0.014, and the 5% interval is from 1.233 to 10.884, and this and for IR.L1 we have 0.62, and the 5% interval, confidence interval, gives us 0.541 to 0.706. The P value is 0, Z value is 14.793, and the standard error is 0.042. IR.L2 is minus 0.0969, standard error is 0.079, Z is minus 1.223, and P is 0.221, and the 5% confidence interval is minus 0.252 to 0.058. IR.L3 is the coefficient is 0.2527. The 5% confidence interval is 0.101 to 0.405, and the standard error is 0.078. Z value is 3.26, and the P value is 0.01. For sigma 2, the coefficient is 301.8307. Standard error is 13.247. The 5% confidence interval is 275.873 and to 327.788. And then we have other things over here. The skew is 1.77. The kurtosis is 17.54. There is a warning. Covariance matrix calculated using the outer product of gradients. Complex step. Okay, so and then we can create some plots to help decipher the above. Model.plot underscore diagnostics of fixed size equal width is 10 and height is 9. plt.show open and close bracket. Now the first graph, there are 4 graphs plotted. The first graph is standardized residual, and we can see that the residuals, the standardized residuals is around 0, but in the year 2020 there are some values, some residuals which are high, very high. And then the second graph on the right shows histogram plus estimated density. So the histogram and the estimated, from the estimated density, the green curve is the normal distribution with the mean 0 and the variance 1, and there is a density curve, and we can see that the density curve is bit taller, bit steeper. And from the histogram we see that there is a highest bar for 0.5 value. Then we look at normal QQ plot, and we have sample quantiles versus theoretical quantiles, and this gives, there are about the skewness. We can see that on the left hand side there are 4 dots, there are 4 data that is away from the normal QK line. Otherwise, so they are lying on the red line, so it's quite good. And the last graph is the correlogram, and from the correlogram we see that all the points are lying around 0, except there is a point at x value equal to 0, and the highest is 1, goes up to 1. So we see from the top left, the residual errors seem to fluctuate around a mean of 0, somewhat uniform variance. So from the phase graph we can see that there are somewhat uniform variance. And from the top right, the density plot suggests an almost normal distribution with mean 0. So we can see this is the green line curve is the normal distribution curve, and the orange curve, which fits the density curve, it is very close to the normal distribution curve with the mean 0. And bottom left QK plot, all the dots should fall perfectly in line with the red line. Any significant deviations would imply the distribution is skewed. Here we are okay. Okay, bottom right, the correlogram ICF plot shows the residual errors are not autocorrelated. Any autocorrelation would imply that there is some pattern in the residual errors which are not explained in the model, which would mean you will need to look for more X's, that is predictors, to the model. So if there is a pattern in the residual errors, then we will need to look for some more predictors. So overall the fit is pretty good. Now to forecast, we will look at the forecast in the next lab.